So let's go ahead and solve this problem. A piston cylinder assembly with a linear spring contains 0.7 kilograms of water initially at 1.5 bar and 20% quality. So there's a lot of information at first sentence. The mass is known, 0.7 kilograms. It's water, so it's given the initial pressure of 1.5 bar at initial quality. Do we use lowercase x for quality? Yes. Quality at state 1 is 20%. Now, this spring up here is described to be a linear spring, which, what does that mean when you say a linear spring? Yeah, that the force that the spring exerts is proportional to its compression. So it's Hooke's law. The force is K times the compression of the spring, or the stretch of the spring, either one. But here the spring is going to be compressed. Okay. The water is heated until the volume occupied by the water is twice its initial volume. Okay. At the final state, the temperature is 280 degrees C. Sketch the process on a pressure volume diagram. Sketch the process on a pressure volume diagram. Well, I'm going to tuck the pressure volume diagram down here, and I know I'm going to run out of room, so bear with me. Please take some good notes if you can. What should I put on that PV diagram? The dome. I should put a dome on. It's typically very steep over here, comes up to the CP. Oh, I forgot the name of that. I remember the acronym CP, but what is it? Critical point, and then it goes very lazily down, and we never show it physically how far that stretches out, but it really does go far out. Okay, you almost have to put on a log plot for the V to make it look real. A lot of times we get a little lazy and we just almost sketch it symmetric. It's not symmetric, but in our cartoon sketch it may look symmetric. All right, now where is my initial state at? First of all, what is the pressure in bar at the critical point? Because I want to kind of feel, is my pressure 1.5 bar, the initial pressure, is it above the critical point pressure for water or below? The critical point pressure for water is around? Yeah. If you can please, for the next few days, bring your tables, you'll get more out of it, because that's this whole chapter, isn't it? You've got to get property data. What's the chapter title? Properties, thermodynamic properties. All right, so if you take a look, it's around 220 bar. 220 bar. Guess where we're at? 1.5. We're way down here. We are way down there, aren't we? And we're 20% quality. So where are we at? Down there. Okay, I was going to ask a clicker question, but I didn't think of it in time. I gave it away, so it's a dud. But there you are. Okay. Now, where is the final state going to be? We have to do a little work. Let's do this. Over here, we're going to have a description of our state, and then we're going to talk about the pressure and the temperature. Those are properties. The specific volume, that's a property, and the internal energy. I just know that those top four we use a lot in this chapter. All right, so I'll talk about at state 1, at state 1, at state 1, and state 1. Now, can you help fill in some of these properties? From the information given, can I see that P1 is 150 kilopascal or 1.5 bar? True? And then they give us down here that it's two-phase, a liquid vapor mixture. Hence, the quality at 1 is 0.20, 20%. Knowing the pressure and the quality, I really have two pieces of information from the state principle. I can get the other properties. Who can tell me the temperature at state 1 and why? Is it the value you're going to tell me it is? Do you got it? It's around 111. degrees C. And why is it 111 degrees C? He knows. Do you? How did he get it to 111? The table, but how? What did he do? Into the table. How did he get it? It's 111.4. Go to table A3. That's the pressure index to the two-phase liquid vapor steam table. And the pressure is a line of 1.5 bar. And the next column is the saturation temperature. And it's two phase. There you go. It's the saturation temperature. How do I get V1? How do I get V1? No. Yeah, it's half of V2, but then how do I get V2? Given the quality, and then I can get V sub G out of the table and V sub F. All at state 1, right? V sub F at state 1, V sub G at state 1, which basically is at 1.5 bar. So I'm going to write this out. The V sub F, if you have the table, it's 0.0010528. Correct me if I'm wrong. Plus 20% times V sub G, 1.159 minus. Then V sub F, 0.0010528. Do you see where I get those V sub F, V sub G values? Right, okay. So we crunch that, and we come up with V sub 1 to be 0.2326 meters cubed per kilogram. Look good? How about U1? Is U1, just to write the equation down, is it U sub F plus the quality 1 times U sub G minus U sub F? Remind me again, what is the subscript F for? Saturated liquid. Subscript G for? Saturated vapor. Exactly correct. So then I just look in the table and I get off the values for U sub F. That would be 466.94. U sub G, 25.1, what is that? 9.7 minus 466.74. Hence, I get a value of U sub 1 when I crunch it away. It's 877.49 kilojoules per kilogram. Can I erase, to save room, how I calculated V1, that equation? Can I erase that? Do you have it down? Yes, sir.
Yeah. The U sub F, the very last one, is that supposed to be 466.94?
Yes, it is. Yes, 94. That's correct. Thank you. But I want to save space here, so can I erase some of the details and leave the final results up? Is that okay? All right, so let's go ahead and just erase right in here, and erase right in here, and then erase right in there. Okay, now, so I was able to deduce T1, V1, and U1. Now the next is I go to the second state, and I don't have a description of the second state. Maybe I'll have to work on that, but what about P2? What about T2? What about V2? What about U2? And possibly, if it's two-phase, X2. I don't know. I'll just put a placeholder there. Maybe it's not applicable. Which of these, starting at the top, do I know P2? Do I know T2? Which one do I know? T2, what is it? 280 degrees C. Now, my friend in the front row, you know what the next property is. Next down from T2 is? And what is it equal to? 2 times V1. What? 2 times V1? It's in the problem statement. How many times do we have to reread those words in the problem statement? So it's heated until the volume occupied by the water is twice its initial volume. Did the mass that's trapped in the piston cylinder change? No. So the specific volume, the volume doubled, the specific volume doubled. So the final specific volume is 0.4653 meters cubed per kilogram. In your calculator, you're going to have more digits, but here I have 4. Knowing these two properties from the state principle, can I maybe get P? Can I get maybe U? Can I maybe deduce what state it's in? This one's tough, but that's chapter 3. Sometimes things are just tough. If you have your tables, can you somebody spend a little time looking in the tables and say, at this temperature, where do I find a specific volume of 0.4653 meters cubed per kilogram? Can you tell me what describe the state? Compressed liquids, two-phase liquid vapor, superheated vapor. Where are we at? I'm going to de-mic and I'm going to walk around and I'll see how many people can do it. You do?
For P2, you got 64.12 bar.
All right. How did you get that pressure? Okay. A2 is a two-phase liquid vapor mixture table. The answer is not in table A2. And it would have been an extrapolation out of A2, not an interpolation, right? Did you do an extrapolation or an interpolation to get that? Well, anyway, it's not right, but it's a good try. Somebody else help me. Come on now. It's over 5 bar or around 5 bar? Around 5 bar. How do you get that? Okay, he's in the right table. A4. What is in table A4? What described the state of the steam in A4? Superheated vapor. It could have gone into the superheated vapor state. If you look in the superheated vapor state, you just kind of move between pressure blocks looking at that line of 280 degrees C until the specific volume is bracketed, the specific volume of 0.4653. True? Is that, let me go to a clean page, insert new page. So table A4, we have a pressure block of 5 bar. We have a pressure block of 7 bar. We have a temperature line of 280, and we have the specific volume at the 5 bar 280. It's 0.5034, and then we have a temperature of 280, and the specific volume for that would to be 0.3574. And what we want is the specific volume to be 0.465284 if you want more digits. Is this value between these two values? And so the pressure, you get the fraction in between. I like to do the interpolation, the linear interpolations, by first getting the fraction. I even say fraction for that. The fraction will be V at all of these are at 280, but it'll be at the 5 bar, 7 bar minus V 280 5 bar divided by, messing it up. This is V 280 7 bar minus V 280 5 bar. This is our value of interest at 280, and we don't know what bar it is. Got it? This fraction, when you put in those numbers, comes in at 0.26107. About 26% of the way. Between what? From 5 bar to 7 bar. So I can calculate the pressure 26.1% of the way, and we find that the pressure is 5.522 bar. That's a linear interpolation. See that? Now, what about the internal energy? Well, the internal energy was 2771.2 and 2766.9. Okay? You can tell that there's not much for the interpolation, but you can get the internal energy U to be interpolated to be 2770.1 kilojoules per kilogram. Does that make sense? So now let's go back to where we were. Oops, not there. We're right here. And let's say this is superheated vapor at 5.52 bar. And the internal energy, 2770.1 kilojoule per kilogram. And what about the quality at state 2? Na. What's Na mean? It's not applicable. The quality is only a property defined in the two-phase region. This is a superheated region. Somebody says, I'll give you like a 1.32 quality. Quality is never over 100%. If you ever calculate a quality that's over 100%, look for an error. Okay. So where is state 2 on this illustration? Outside the dome, there's state 2. There's 5.5 something tube, and the temperature's up, and the specific volume actually doubled. So if I tried to draw it to scale, I should have this maybe like right there, something. But that doesn't look to scale at all, does it? I'm trying to match the change in specific volume doubled. But there you go. What does the process look like? Because it's a linear spring, right? The linear spring, as it gradually increases, the pressure increases linearly below it. Is that a good PV diagram? You like it? All right. Part B, calculate the work and the heat transfer for the processes, or for this process. All right. So I want to calculate Q 1 to 2 and work 1 to 2. Both of those I want to calculate. Which one should I try to calculate first? The heat transfer or the work transfer? Let's try the work first, okay? How am I going to calculate the work first? Maybe I pause and I walk around, and I'm not going to move on until I get 5 people show me the way to do it correctly on their paper with their notes, okay? Because there's no sense watching me. All right, well, the work is the integral PdV, cap V, right? It's the integral P, well, look at this. How about, can I put P average here? It's just the area under the curve, the average pressure, times the volume change. Well, I'll put mass times V final minus V initial. All right? So we'll put in I need to scoot down. I'm really sorry, but I need the room. I'll scoot down a little bit. It's 552 kilopascal minus 150, well, add those, kilopascal, divided by 2. Is that the average pressure? 552 plus 150 divided by 2, is that the average pressure? All right. And then the mass was 0.7 kilograms of water. And then the final volume, 0.4653 minus the initial volume, 0.2326 meter cubed per kilogram. Did I emphasize that you need to be very careful with units? Did I say that unit errors on exams are just, you might as well consider them fatal? I mean, no student is happy for the amount of partial credit given when they make trivial errors on units. That's it, okay? So you got to get, and they're easy to get rid of. Just by being careful, you can get rid of unit errors. All right, and then we recall that a kilojoule is a kilopascal times a meter cubed. True or false? I did that before, right? So kilopascal, meter cubed, kilojoules, I think the units are all there. And what do we work out? How many people can work this out to be 57.2 kilojoules rounded off to 3 significant digits, 57.2. Answer for that part. What's the next part? How do I find Q1 to 2? Go to the first law for the process, which is Q1 to 2 minus work 1 to 2 is equal to the mass lowercase u2 minus u1. True? And so Q1 to 2 is equal to the work 1 to 2 plus the mass u2 minus u1, which is 57 point. This time we put in more digits, kilojoules for the work, plus the 0.7 kilogram times u2, which is 2770.1 minus u1, 877.49 kilojoules per kilogram. Cancel the kilograms. We have consistent units. Q, 1 to 2, is a whopping 1,382 kilojoules, 4 significant digits. You'll never lose any points, but give me a fifth and you lose some points. This is really pushing the limit on how accurate we really are. Okay? But you won't lose points with 4. 3 is better. If you round it off to 3, there you go. Got it? Both would be graded equivalently. Any questions about the problem?